ಇದು ಮಾಹಿತಿ ಖಜಾನೆ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿ.
ಮಾಹಿತಿ ಖಜಾನೆ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿಗೆ ನನ್ನೆಲ್ಲ ಸಂಯುಕ್ತರಿಗೂ ಆತ್ಮೀಯವಾದ ಸ್ವಾಗತ. ಇಂದು ನಾವು ಮತ್ತೊಂದು ಉಪಯುಕ್ತ ಮಾಹಿತಿಯೊಂದಿಗೆ ಬಂದಿದ್ದೇವೆ. ಈ ವಿಡಿಯೋ ನಿಮಗೇನಾದರೂ ಇಷ್ಟವಾದಲ್ಲಿ ಲೈಕ್, ಶೇರ್, ಕಾಮೆಂಟ್ ಮಾಡಿ ಹಾಗೂ ಇನ್ನು ಹೆಚ್ಚು ಉಪಯುಕ್ತ ಮಾಹಿತಿಯನ್ನು ನಮ್ಮ ಯೂಟ್ಯೂಬ್ ವಾಹಿನಿಯಿಂದ ಏನಾದರೂ ನಿರೀಕ್ಷಿಸುತ್ತಿದ್ದೀರಾ? ನಿರೀಕ್ಷಿಸಿದಲ್ಲಿ ಬೆಲ್ ಐಕಾನ್ ಅನ್ನು ಕ್ಲಿಕ್ ಮಾಡುವುದರ ಮೂಲಕ ಸಬ್ಸ್ಕ್ರೈಬ್ ಆಗಿ.
Security GSM offers several security services using confidential information stored in the AUC and in the individual SIM. The SIM stores personal, secret data and is protected with a PIN against unauthorized use. 3 algorithms have been specified to provide security services in GSM. Algorithm A3 is used for authentication, A5 for encryption, and A8 for the generation of a cipher key. The various security services offered by GSM are access control and authentication. The first step includes the authentication of a valid user for the SIM. The user needs a secret PIN to access the SIM. The next step is the subscriber authentication. This step is based on a challenge-response scheme as shown below. Mobile network SIM RAND K RAND K AUC 128 bit 128 bit 128 bit 128 bit A3 SIM SIES 32 bit SIES 32 bit Master of Science SIES equals SRES SRES 32 bit SRES K Individual Subscriber Authentication Key SRES. Signed Response Subscriber Authentication is based on the SIM, which stores the individual authentication key K, the user identification IMSI, and the algorithm used for authentication A3. The AUC performs the basic generation of random values RAND, signed responses SRES, and cipher keys K, for each IMSI, and then forwards this information to the HLR. The current VLR requests the appropriate values for RAND, SRES, and K, from the HLR. For authentication, the VLR sends the random value RAND to the SIM. Both sides, network and subscriber module, perform the same operation with RAND and the key K, called A3. The MS sends back the SRES generated by the SIM. The VLR can now compare both values. If they are the same, the VLR accepts the subscriber, otherwise the subscriber is rejected. Confidentiality. All user-related data is encrypted. After authentication, BTS and MS apply encryption to voice, data, and signaling as shown below. Mobile network, BTS, MS with SIM RAND CRAND plus RAND AUC 128 bit 128 bit 128 bit 128 bit SIM AB AS cipher key 64 bit BTS A5 64 bit encrypted data MS to ensure privacy. All messages containing user-related information are encrypted in GSM over the air interface. After authentication, MS and BSS can start using encryption by applying the cipher key K, which is generated using the individual key K, and a random value by applying the algorithm A8. Note that the SIM in the MS and the network both calculate the same K, based on the random value RAND. The key K itself is not transmitted over the air interface. MS and BTS can now encrypt and decrypt data using the algorithm A5 and the cipher key K, anonymity. To provide user anonymity, all data is encrypted before transmission, and user identifiers are not used over the air. Instead, GSM transmits a temporary identifier, TMSI, which is newly assigned by the VLR after each location update. Additionally, the VLR can change the TMSI at any time. New data services to enhance the data transmission capabilities of GSM, 2 basic approaches are possible. As the basic GSM is based on connection-oriented traffic channels, e.g., with 9, 6 kbit s each, several channels could be combined to increase bandwidth. This system is called HSCSD, high-speed circuit switched data. A more progressive step is the introduction of packet-oriented traffic in GSM, i.e., shifting the paradigm from connections, a telephone thinking to packets, the Internet thinking. The system is called GPRS, General Packet Radio Service. 21. HSCD, a straightforward improvement of GSM's data transmission capabilities, is high-speed circuit switched data, HSCSD, in which higher data rates are achieved by bundling several TCHs. An MS requests one or more TCHs from the GSM network, i.e., it allocates several TDMA slots within a TDMA frame. This allocation can be asymmetrical, i.e. more slots can be allocated on the downlink than on the uplink, which fits the typical user behavior of downloading more data compared to uploading. A major disadvantage of HSCD is that it still uses the connection-oriented mechanisms of GSM, which is not efficient for computer data traffic. GPRS, the next step toward more flexible and powerful data transmission, avoids the problems of HSCSD by being fully packet-oriented. The General Packet Radio Service, GPRS, provides packet mode transfer for applications that exhibit traffic patterns such as frequent transmission of small volumes, e.g., typical web requests, or infrequent transmissions of small or medium volumes, e.g., typical web responses, according to the requirement specification. For the new GPRS radio channels, the GSM system can allocate between 1 and 8 time slots within a TDMA frame. Time slots are not allocated in a fixed, predetermined manner, but on demand. All time slots can be shared by the active users. Up and downlink are allocated separately. Allocation of the slots is based on current load and operator preferences. The GPRS concept is independent of channel characteristics and of the type of channel, traditional GSM traffic or control channel, and does not limit the maximum data rate. Only the GSM transport system limits the rate. All GPRS services can be used in parallel to conventional services. GPRS includes several security services such as authentication, access control, user identity confidentiality, and user information confidentiality. The GPRS architecture introduces 2 new network elements, which are called GPRS support nodes, GSN, and are in fact routers. All GSNs are integrated into the standard GSM architecture, and many new interfaces have been defined. The Gateway GPRS Support Node, GGSN, is the interworking unit between the GPRS network and external packet data networks, PDN. This node contains routing information for GPRS users, performs address conversion, and tunnels data to a user via encapsulation. The GGSN is connected to external networks, e.g., IP or X25, via the G interface and transfers packets to the SGSN via an IP-based GPRS backbone network, G interface. The other new element is the Serving GPRS Support Node, SGSN, which supports the MS via the Go interface. The SGSN, for example, requests user addresses from the GPRS register, GR, keeps track of the individual MS's location, is responsible for collecting billing information, e.g., counting bytes, and performs several security functions such as access control. The SGSN is connected to a BSC via frame relay and is basically on the same hierarchy level as an Master of Science. The GR, which is typically a part of the HLR, stores all GPRS relevant data. SGSN, MSBSS, SGSN, GGSN, PDN, a Master of Science HLR, GRVLR, EIR GPRS architecture reference model, as shown above. Packet data is transmitted from a PDN via the GGSN and SGSN directly to the BSS and finally to the MIS. The Master of Science, which is responsible for data transport in the traditional circuit switched GSM, is only used for signaling in the GPRS scenario. Before sending any data over the GPRS network, an MS must attach to it, following the procedures of the mobility management. The attachment procedure includes assigning a temporal identifier, called a temporary logical link identity (TLLI), and a ciphering key sequence number (CKSN) for data encryption. For each MS, a GPIS context is set up and stored in the MS and in the corresponding SGSN. Besides attaching and detaching, mobility management also comprises functions for authentication, location management, and ciphering. The following figure shows the protocol architecture of the transmission plane for GPIS. All data within the GPIS backbone, i.e., between the GSNs, is transferred using the GPIS Tunneling Protocol, GTP. GTP can use two different transport protocols, either the reliable TCP, needed for reliable transfer of X25 packets, or the non-reliable UDP, used for IP packets. The network protocol for the GPIS backbone is IP, using any lower layers. To adapt to the different characteristics of the underlying networks, the Subnetwork Dependent Convergence Protocol, SNDCP, is used between an SGSN and the MIS. On top of SNDCP and GTP, user packet data is tunneled from the MS to the GGSN and vice versa. To achieve a high reliability of packet transfer between SGSN and MS, a special LLC is used, which comprises ARQ and FEC mechanisms for PTP and later PTM services. 23. MSBSS SGSN GGSNU OP IPX 25 IPX 25 SNDCP GTP SNDOP GTP LLC LLG UDP TCP UDP TCP ALC BSSGP IP IP RLC BSSGP MAC MAC FR FAR L1 12 L1 L2 Radio GPIS Transmission Plane Protocol Reference Model A Base Station Subsystem GPIS Protocol BSSGP is used to convey routing and QoS related information between the BSS and SGSN. BSSGP does not perform error correction and works on top of a frame relay FR network. Finally, radio link dependent protocols are needed to transfer data over the interface. The radio link protocol, RLC, provides a reliable link, while the MAC controls access with signaling procedures for the radio channel and the mapping of LLC frames onto the GSM physical channels. The radio interface at needed for GPIS does not require fundamental changes compared to standard GSM. 24. Unit 2 Wireless Medium Access Control Motivation for a specialized MAC, hidden and exposed terminals, near and far terminals, SDMA, FDMA, TDMA, CDMA. The Media Access Control MAC, Data Communication Protocol Sublayer, also known as the Medium Access Control, is a sublayer of the data link layer specified in the 7-layer OSI model, a layer 2. The hardware that implements the MAC is referred to as a Medium Access Controller. The MAC sublayer acts as an interface between the Logical Link Control, LLC, sublayer and the network's physical layer. The MAC layer emulates a full duplex logical communication channel in a multi-point network. This channel may provide unicast, multicast or broadcast communication service. Logical Link Control, LLC, Data Link Layer Media Access Control, MAC, Physical Layer Transmission Medium IEEE Standard Physical Layer Transmission Medium Internet Model LLC, and MAC Sublayers Motivation. For a specialized MAC, one of the most commonly used MAC schemes for wired networks is Carrier Sense Multiple Access, with Collision Detection, CSMA-CD. In this scheme, a sender senses the medium, a wire or coaxial cable, to see if it is free. If the medium is busy, the sender waits until it is free. If the medium is free, the sender starts transmitting data and continues to listen into the medium. If the sender detects a collision while sending, it stops at once and sends a jamming signal. But this scheme doesn't work well with wireless networks. The problems are, signal strength decreases proportional to the square of the distance the sender would apply CS and CD, but the collisions happen at the receiver. It might be a case that a sender cannot hear the collision, i.e., CD does not work. Furthermore, CS might not work, if for e.g., a terminal is hidden and exposed terminals. Consider the scenario with 3 mobile phones as shown below. The transmission range of A reaches B, but not C. The detection range does not reach C either. The transmission range of C reaches B, but not A. Finally, the transmission range of B reaches A and C, i.e., A cannot detect C and vice versa. Hidden terminals A, B, C. A sends to B, C cannot hear A. C wants to send to B, C senses A. Free medium, CS fails, and starts transmitting. Collision at B occurs. A cannot detect this collision, CD fails, and continues with its transmission to B. A is hidden from C and vice versa. Exposed terminals B sends to A, C wants to send to another terminal, not A or B. Outside the range, C senses the carrier and detects that the carrier is busy. C postpones its transmission until it detects the medium as being idle again, but A is outside radio range of C. Waiting is not necessary. C is exposed to B. Hidden terminals cause collisions, whereas exposed terminals causes unnecessary delay. Near and far terminals. Consider the situation shown below. A and B are both sending with the same transmission power. A, B, C. Signal strength decreases proportional to the square of the distance. So, B's signal drowns out A's signal, making C unable to receive A's transmission. If C is an arbiter for sending rights, B drown out A's signal on the physical layer, making C unable to hear out A. The near-or-far effect is a severe problem of wireless networks using CDM. All signals should arrive at the receiver with more or less the same strength, for which precise power control is to be implemented. SDMA Space Division Multiple Access, SDMA, is used for allocating a separated space to users in wireless networks. A typical application involves assigning an optimal base station to a mobile phone user. The mobile phone may receive several base stations with different quality. A MAC algorithm could now decide which base station is best, taking into account which frequencies, FDM, time slots, TDM, or code, CDM, are still available. The basis for the SDMA algorithm is formed by cells and sectorized antennas, which constitute the infrastructure implementing space division multiplexing, SDM. SDM has the unique advantage of not requiring any multiplexing equipment. It is usually combined with other multiplexing techniques to better utilize the individual physical channels. FDMA frequency division multiplexing, FDM, describes schemes to subdivide the frequency dimension into several non-overlapping frequency bands. Code N. Frequency time frequency division multiple access is a method employed to permit several users to transmit simultaneously on one satellite transponder by assigning a specific frequency within the channel to each user. Each conversation gets its own, unique, radio channel. The channels are relatively narrow, usually 30 kHz or less, and are defined as either transmit or receive channels. A full duplex conversation requires a transmit and receive channel pair. FDM is often used for simultaneous access to the medium by base station and mobile station in cellular networks, establishing a duplex channel. A scheme called frequency division duplexing, FDD, in which the two directions, mobile station to base station, and vice versa, are now separated using different frequencies. 900 MHz 124 935. 2 MHz 915 MHz 890. 2 MHz 200 kHz 20 MHz FDM, for multiple access, and duplex. The two frequencies are also known as uplink, i.e., from mobile station to base station, or from ground control to satellite, and as downlink, i.e., from base station to mobile station or from satellite to ground control. The basic frequency allocation scheme for GSM is fixed and regulated by national authorities. All uplinks use the band between 892 and 915 MHz. All downlinks use 935 to 960 MHz. According to FDMA, the base station, shown on the right side, allocates a certain frequency for up and downlink to establish a duplex channel with a mobile phone. Up and downlink have a fixed relation. If the uplink frequency is f equals 890 MHz plus n0, 2 MHz, the downlink frequency is f equals f plus 45 MHz, f equals 935 MHz plus n0, 2 MHz for a certain channel n. The base station selects the channel. Each channel, uplink and downlink, has a bandwidth of 200 kHz. This scheme also has disadvantages. While radio stations broadcast 24 hours a day, mobile communication typically takes place for only a few minutes at a time. Assigning a separate frequency for each possible communication scenario would be a tremendous waste of scarce frequency resources. Additionally, the fixed assignment of a frequency to a sender makes the scheme very inflexible and limits the number of senders. TDMA, a more flexible multiplexing scheme for typical mobile communications, is time division multiplexing, TDM. Compared to FDMA, time division multiple access, TDMA, offers a much more flexible scheme, which comprises all technologies that allocate certain time slots for communication. Now synchronization between sender and receiver has to be achieved in the time domain. Again, this can be done by using a fixed pattern similar to FDMA techniques, i.e., allocating a certain time slot for a channel, or by using a dynamic allocation scheme. One code frequency time L. Listening to different frequencies at the same time is quite difficult, but listening to many channels separated in time at the same frequency is simple. Fixed schemes do not need identification, but are not as flexible considering varying bandwidth requirements. Fixed TDM, the simplest algorithm for using TDM, is allocating time slots for channels in a fixed pattern. This results in a fixed bandwidth and is the typical solution for wireless phone systems. MAC is quite simple, as the only crucial factor is accessing the reserved time slot at the right moment. If this synchronization is assured, each mobile station knows its turn and no interference will happen. The fixed pattern can be assigned by the base station, where competition between different mobile stations that want to access the medium is solved. 417 US 1. 23 *** 11 12 2. 3 11 12 downlink uplink. The above figure shows how these fixed TDM patterns are used to implement multiple access and a duplex channel between a base station and mobile station. Assigning different slots for uplink and downlink using the same frequency is called time division duplex, TDD. As shown in the figure, the base station uses 1 out of 12 slots for the downlink, whereas the mobile station uses 1 out of 12 different slots for the uplink. Uplink and downlink are separated in time. Up to 12 different mobile stations can use the same frequency without interference using this scheme. Each connection is allotted its own up and downlink pair. This general scheme still wastes a lot of bandwidth. It is too static, too inflexible for data communication. In this case, connectionless, demand-oriented TDMA schemes can be used.